because we do have a nice sunny day out today. So continuing our forest tour, this is the Bartlett Experimental Forest in New Hampshire. You can tell I like fall. We have lots of fall pictures. So here we're going to talk about, we're going to kind of walk through, I called it calculating change. We're going to talk about calculating change and comparing alternatives. We're also going to walk through that biomass factor equation, and I'll show you an example of an actual biomass equation, just so you can see how things work. And again, if you're staying for the exercise, this is the map we'll be doing, but just take a look at it. It's not so bad. So our roadmap, this is the roadmap for live biomass, because that's mostly what we've been talking about today. And it's a pretty straightforward roadmap, so you're going to pick your area of interest, because again, this approach will work no matter what your spatial scale is. You're going to pick your carbon pools to estimate. Right now, we're talking about biomass, but these steps would apply for any pool. Locate the data. If you're lucky enough to have any data, probably you're going to have to inventory. Then you're going to pick your method. So remember this morning we talked about you can take that volume approach with that biomass expansion factor, or you can go with those allometric equations, those biomass equations where you need species and diameter. So you're going to decide what approach is best for you, and again, you may not have a choice. If you don't have those STEM data, you're going to have to go with volume. And we had a good discussion this morning about equation choice and errors, so you may want to use that biomass expansion factor approach if you're not confident about the equations that are available to you. So then you just apply your method, don't forget your roots, and scale up to the area of interest. So often if we stratified, we might have volume data for conifers that are 40 to 60 years old, and we might know how many hectares we have in that. And so we might do that as a separate calculation, and we have a per hectare value, and then we multiply out and scale that up. So that's our basic roadmap that we apply no matter how we're going about things. So first we're going to talk about this biomass expansion factor approach. And again, these two methods, either one is acceptable. It just really depends on your situation. Do you have a question?
No, I'm sorry.
Okay.
Forgive me. I should glue my head.
That's all right. Just wave at me if you're. Yep. So this one, your input volume is again merchantable volume. So this is really important. It's merchantable volume because the factor will scale up to total volume. So those branches, tops, stumps, non-merchantable stems. So you're sort of expanding it twice if you're using total volume data. So you want to make sure you have cubic meters per hectare, merchantable volume. Then if you're using these factors in the IPCC guidance, they are a one-stop shop. That expansion factor includes everything you need. If you're using a factor that you found in the literature, it may not include wood density. Those values are in the IPCC guidance, so you want to make sure you include that step. We don't need to do that today, but you might need to. I'm going to multiply by percent carbon. To get tons of carbon, again, 50% is a good round value. There are values in the IPCC guidance, and you can look them up, and they vary a little bit. And then again, if you have a separate step for your below-ground biomass, you want to do that. This equation from the guidance includes everything you need. So here's what it looks like. This is 2.8E from the IPCC guidance, and again, this is in volume 4. It's on your flash drive, and it looks a little scary, but it's not. It just takes care of everything in one step. So here I've defined what everything is, and this is all written out in the guidance as well. I've taken this directly from that. And now we're going to kind of walk through with some data and a color-coded example so that you can see what goes where. You can see just how straightforward this approach really is. So this is the stand, yes?
In the previous slide, I suspect the V represents volume. That's it's not, we didn't define it on this slide.
Oh, I did leave it off, didn't I? Yes, it's using merchantable volume.
Okay, thank you.
So here it's color-coded. This is a stand in Pennsylvania. That's a picture of the actual stand. And so I put this in the proper units. So there's 284.4 cubic meters per hectare of merchantable volume in a 12-hectare stand. So if you look at that example, you can see I've kept the colors all the same, and everything comes right out of that guidance. So you just go to the table, and you look up. In this case, they have very generic biomass expansion factors for things in North America. They're very much more detailed for other regions, but we have access to a lot of them. So these are quite general. And so it was an equation for deciduous species, and they were sorted out by stocking level. So it'll be one expansion factor if your trees are quite dense, and it's a different factor if you have fewer trees. So you go right to the table, and again, in the exercise, we can do that, and you can see how that works, because you don't want to do that. The root to shoot ratio is also, you simply look it up in a table, and then multiply it out by the area. So you can see that's really not very difficult.
I'm just curious why it's 1 plus the ratio, not 1 minus the ratio.
It's just because of the way it depends on the way the ratio is constructed. I mean, I actually did work this out 2 different ways to make sure, because I had that same thought. And it's just the way they structured the equation. If you were doing it in separate parts, you might do it differently, but it depends on whether it's root to shoot or shoot to root. But I did actually compute it out all in individual parts, because it looked odd to me at first too.
It still looks really strange even with that explanation, because you're grossing it up by 1, 2, 4. So I'm not sure why would you be grossing it up by the ratio. I'm just trying to understand the logic of the equation.
Normally, when I do it by hand, I would calculate that percentage of roots separately, and then it's a proportion of the above ground biomass, and then I would add it, but they just combined it all into one. So it has that structure, and again, it did look really odd because that's not how I set it up, but when I did break it into pieces, I did get the same, because I was quite concerned. Because it looks really funny, but it does actually work. If I do it different ways, I still get that number. I know. I was concerned at first too, because it's not the structure how I would normally put it together, but I actually did it twice because it looked odd to me as well. I did it again. There we go.
Yeah, I think what you said actually explained the formula. What it is that if you were to remove 1, what you'll actually be doing is taking the volume to be less than, the value that you get by multiplying V and BCF, that would normally it will give you 100. So by adding that factor, you are now dealing with the root component.
I often do it in 2 separate steps, and then it's quite clear when you can see it, but they just implemented it into one equation. It does look quite odd. So our big question, the one we always want to know is, well, okay, how much carbon is our forest storing? So remember we talked about measured boxes, so we're just going to measure the boxes at 2 different points in time. It might be 5 years, it might be 10 years. That is a question of choice. So all we do is take the difference, and that's equivalent to measuring the arrows. And again, this is a net because we're measuring the boxes. It's that net change over time. You can see this in absolute terms, so it might be for the whole 12-hectare area or whatever your area is, a province, a state, a district. More commonly, I tend to work on a per area basis. It's a lot easier to do that and to compare things when you're on a per area basis than dealing with these large numbers when you scale up to include that area. But that's always just something to pay attention to see which of those you're on. So this is really straightforward. We have time 2 minus time 1. Okay, but what does that tell you? So that's net change of whatever your time period was. But that doesn't really tell you anything about the rate, does it? And if you want to compare, one of the things I like to do is compare different management treatments. Maybe we try different thinning types. Maybe you might want to compare if you're thinking about replanting, you might want to know what forest types store the most carbon if if you have a choice of several that are appropriate. So how would you compare these if all you have is this net number? I mean, if you're comparing stands that started in very different places, maybe one had a lot more carbon or one was a lot older, just using that net, it doesn't really quite give you all the information that you need. So I call this average annual change. It's a lot like a timber yield. People have different names for it. But this is really, you do want to do those net changes in the stocks. That's important. But this is really helpful when you want to make any kind of comparison. So if you want to compare management treatments, age classes, forest types, perhaps different regions of your country, whatever you might want to compare, this is how you do it. So you're still going to take your time 2 minus your time 1. And then you're just going to divide by whatever the number of years between measurements is. And usually we do express this on a per area basis. So it would be tons of carbon per hectare per year. So we're annualizing even though we only have 2 measurements. This is really what enables us to make all these different comparisons. Now we're looking at the rate side of things, we're looking at a rate of change, and we can put everything on an equal playing field and we can compare things. So I find this is really a useful thing to do. And I just worked it out here. I mean, it's really straightforward. It's just time 2 minus time 1, and again, those are whatever you have chosen them to be. It may simply be whatever data you have available, what you measured, and then you just divide by the number of years in that interval. And in this case, we come up with 2.43 tons of carbon per hectare per year. So now, this is in Pennsylvania, and actually, this forest here used to look like the other one. And in 1985, a very large tornado put an end to that. So this is 15 years later, what that area looks like. So obviously, we have a lot more carbon in that forest right now. We don't have very much at all in that one. We could measure those trees, and we would need quite a job. But there's not going to be very many tons of carbon out there. But the rate at which those stands are accumulating carbon would be quite different, right? Because the one is 15 years old, and the other one is actually about 175 years old. So we couldn't really, if we just had that net, it really wouldn't tell us very much. But when we have average annual change, now we can make these types of comparisons.
So just out of curiosity, because I'm trying to get an understanding of the scale. Just out of curiosity, I'm trying to get an understanding of the scale and the amount of carbon that can be sequestered in the forest. Using that example, have you got any idea of what rate that was per acre that was sequestered?
Now I'm going to get into trouble because in the US, forestry is in English units. And I'm always having to convert back and forth. So what pops into my head, I can sometimes not quite remember. I think, because I'm always usually in tons per acre, I think usually about a ton, an English ton per acre per year for northeastern forests is fairly typical. But again, this really varies because say in the southeastern United States where we have a lot of pine that grows quite fast, you know, and I think in New Zealand like radiata pine would grow quite fast, you're going to have a very different number. And a younger stands would be much faster. You can be down to about a half a ton in older stand per acre per year.
So what would be the maximum? So I'm just thinking of a carbon price of $8 a ton for argument's sake.
You know,
if you're getting $8 an acre, it doesn't make much sense.
I honestly can't answer that question because I'm not as familiar with the productivity of the tropical species.
It's about 0.3 tons per 0.3 tons per hectare per year.
0.3 tons
Per hectare per year.
per hectare per year.
Out of curiosity, then the example you out of curiosity, the example you used before when you're looking at the damaged forest with the regeneration or plant and the age difference. Now you said the younger forest would be accumulating at a faster rate than the old forest, which would probably reach close to steady state as opposed to depends on the age. Now, if I were to measure, and I want to measure, let us say we put in a new plantation of native species, mixed native species. At what stage should we set a baseline to determine the age of this young forest, whether it's at 5 years, 10 years, 15 years? And then if you're looking at the age to maturity for harvesting, some of our rapid growing species we can harvest in 20 years. So to get a sense, I don't know if there's a ballpark figure that you take your full set of measurements to calculate the rate at which a young plantation accumulates. Or is it some sort of continuous measurement you have to do?
So really, until you could have a diameter at breast height, you wouldn't take a measurement. So you have to wait. Most of the time, 2.5 centimeters is sort of where you start. You usually don't measure trees that are smaller than 2.5 centimeters. There's really not much carbon in them. It's extremely time consuming to, like that stand with all those tiny little stems, you would not inventory that stand at that point. You would wait more till it got to its stem exclusion and you had stems that were more like 5 or 6 centimeters. Just because of the trade-off in time.
In our forests, you get 5 centimeters in 2 years.
Then as long as when you have that diameter at breast height, but usually not less than 2.5 centimeters. And often because the equations, there simply aren't any equations that are valid for anything under that 2.5 centimeters. So it's going to depend on your situation, but you wouldn't measure generally until you had a breast height. It would not be worth the cost for the amount of carbon there.
From our experience with the improves, for 3-year-old Rhizophora, it's about 4 tons per hectare. It's below 5 cm. It's not at DBH, breast height.
Using root collar?
Yes.
So that is an alternative. Sometimes you measure at root collar. But when you have a lot of small stems, it's extremely time intensive to inventory them. So you might do smaller subplots. So you always do have that trade-off. So again, that there's no set answer. And if you're at 2 years, you have trees that are 5 centimeters, that might be a case where you inventory less than every 5 years. It may be worth it in your situation to do that. So we are back to our roadmap here, just so we have this if we're doing the exercise. So you need your data. Probably you're going to have to take some inventory. If you're lucky, there's data out there. You might need height, and a lot of times you can calculate height as well. There are equations to calculate height. Find your equations. Again, we talked a lot this morning about the importance of selecting equations that are appropriate. It can introduce a lot of error otherwise. Then you just go ahead and calculate them out. One note, there are some equations I have seen that actually are for green biomass. So I always like to make a point to make sure that you are calculating dry biomass. It doesn't happen often, but it can happen. And you want to multiply by your percent carbon, and again, watch the units. A lot of the step-by-step, the one I'll show you later, give you kilograms. So you need to use diameter in centimeters, and you get kilograms, so you have to make sure in the end you get to your tons. You can never talk about units too much. It's worse in the United States because if I'm talking with ecologists, then I'm all in metric tons per hectare. If I'm talking with foresters, it's tons per acre. And tons, you know, the abbreviation for tons, there's a lot of different ones. So you're kind of, is that a metric ton? Is that an English ton? You can never be too careful about your units. And as long as I've done this, I still screw it up sometimes and have to go back and double check it again. So when in doubt, ask, double check, triple check your units. I cannot say that enough. So just a few general notes on biomass equations. Again, we talked a lot about this morning. So this is a stem by stem, unlike the volume, which is aggregated. So you're going to calculate and then sum. A lot of different forms of these equations, a lot of different mathematical forms they can take. They all do perform a little differently. Again, we had some good discussion on that this morning. You do have to kind of keep in mind that every equation behaves differently, and so some of the differences in the results could be due to the behavior of the equation. And it's really important. You can see, I've stuck it there in red. We talked about this a lot. The range, when you have the paper that describes the equation in the journal article, it should give you all the details, including the diameter range of stems that equation was built on. So you should have that information in. It's okay if you're a little outside that range, but you want to make sure that you're really not well outside the range of diameters that were used to construct the equation. You also, as I said, you don't want to calculate a larch using a southern pine equation, and you want to make sure you're as close to the region as possible. So this is just, this is the equation I use. It's a set of 10 equations that were developed, and they apply to the entire United States, and there's 10 of them, and they're by species groups. So there's one equation that's used for oaks, hickories, and hard maples. So it doesn't matter if it's a sugar maple or a red oak, you use the same equation. And some people get a little stressed because they're not very specific, but a lot of work has been done. They were compiled from all the available equations. And they actually do fit fairly well. It seems odd that a southern pine could be calculated with the same equation you use for a lodgepole pine. But they were developed for national use so that you didn't have to worry that calculating a red maple with an equation from New Hampshire and you'd get a really different answer with the same diameter red maple from a Wisconsin equation. So these were developed to kind of remove that source of error and be nationally consistent.